So my name is Avishai. It's over here on the board. And I'm going to be talking to you about mathematics, specifically the mathematics of reliability. And the link over here is to a companion Jupyter notebook, IPython notebook. It's actually hosted on GitHub. This is a redirect. So if you have a laptop, then click on it. If not, you can just do it at home or whatever you want. The notebook contains a lot of information. It's actually more elaborate than what is on the slides. You can just do it as a workshop offline or whatever you want. I'm also accepting pull requests. So if you feel like you want to add to it or whatever, then feel free. Maybe I said something stupid there and you want to correct me, I don't know. So have fun. This is a talk about reliability. So I have to say in advance that reliability is intimately linked to culture. And this is like a totally different talk. So I'm focusing on the technical aspects of reliability here. So don't think like this is all there is to it or something like that. The purpose of this talk is to get people to think about reliability in an analytical way. So I don't know how people here do reliability. I try to do it in an analytical way and use mathematics to my advantage. So let's begin. Who likes math? That's actually more people than I expected. Who doesn't like math? Oh, come on. Seriously? So most people don't like math, or apparently laptops. Okay? And the normal reaction that I get when I speak to people about mathematics is this. Yeah. People are afraid of mathematics. This is not a secret. People shouldn't be scared of mathematics. Mathematics is actually not that hard. The reason people are afraid of mathematics is first because sometimes they had lousy teachers, and second because they see too many numbers, too many formulas. So when I thought about this talk, I went to talk to one of my friends who's a math doctorate, and what he told me was, listen, the formulas are not important, the numbers are not important. What's important are the models and the thought process. That's what's important in math. So you are going to see some formulas because you have to put something on the slides, but that's not the important part. Mathematics is about formalizing. It's about formalizing your thought process, and it's about formalizing your assumptions. It's about modeling, and it's about proving stuff. And what happens when you formalize and you prove stuff, you often find that you neglected something. There's something you haven't thought about. There's a loophole somewhere. And that's the important part. This is where we gain our insights, very important insights that we wouldn't get any other way. So there's a story about this math professor that in the middle of a lecture wrote something on the board and said, this is trivial, that, blah, blah, blah. And then looked back and oh, wait. 45 minutes later, it turns back, oh, yeah, it's trivial, and continues. So that stuff actually happens. Every once in a while, you go this is trivial, and then you think back on it, and it's like, wait, this is actually not so trivial. So this is very important. So let's start with an example to justify why we actually do this stuff. So a lot of people use Nagios, and they monitor stuff like their service, like their API or the web service or whatever it is they have. And Nagios is, the way Nagios works is that you check your service, say, every 15 seconds or whatever, and if the check fails, then you don't get an alert immediately, because otherwise you would get tons of alerts because of false positives, like every network problem would raise an alert. So you set it to something like max check attempts to 4, and after you had 4 consecutive failures, only then you get an alert. So suppose we have our service is experiencing 50% failure, which is actually very, very high. Normally in a production system, you'd see something like 10%, 20%, all complete failure. So this is what the fuck? Yeah, failure, see? No, this is not Linux, actually. This is the physical layer. Yeah, but thanks. I'm getting a Mac. Awesome. So this is actually a pretty let's say lenient use case, and let's calculate the chances of getting of the check, like 4 consecutive check actually failing. So the probability of getting to a hard critical state in every minute is 2.6%. That's it. That's like horribly low. And the chances of not getting an alert, like every minute we check it again and again and again, so eventually we would get an alert. But the chances of getting an alert in half an hour are only 45, of not getting an alert in half an hour is 45.9%. And even after an hour and a half, there's still about 10% chance of not getting any alert. So this is like horrible. And people do this all the time, because they never computed the math of how this works. So if you want to monitor your service or anything that has statistical failures, you shouldn't be using Nagios plugins this way. You should either outsource the logic of the test to your plugin and only have Nagios run the test, or use something entirely different, or monitor graphic metrics that operate on a time window, something like that. So the important takeaway here is that Nagios is not designed to test statistical failures or anything that has false negatives, for that matter. So this is why we need math, to know those things. So let's talk about reliability. Anybody wants to define reliable? Anybody? What terms do you use for the reliable? Yeah. Okay, MTBF, yeah. SLA, failure per year, QoS, all those fancy numbers we see on contracts. So what's the problem with those definitions? So what does 4 nines mean? 4 nines of what? Of uptime, right? What is uptime? So what is uptime? If my service has 1.5 seconds latency, is my system up? Depends, right? So I don't know, maybe. If it's 4 seconds, is my system still up? Again, I don't know. If I have 50% error rate, is my system up? So those terms by themselves are not enough to define reliable. To actually define those things, we need to define failure first. And that's a very big problem. How do we define failure? So we have like the engineering people who define this very easily as the system operating outside specified parameters. And that's like a great definition for me. You give me parameters. If the system is working within parameters, then it's okay. If not, it's failing. Awesome, very easy. But how do I set the parameters? To set the parameters, I have to know the business use case. That's the important part. Our systems have a purpose, and to define the parameters, we need to understand the purpose of the system. If the system doesn't have throughput, it doesn't generate any money, then it's useless. But in reality, and anyone who does the business would tell you, the definition of failure is that users are complaining. So you don't get to decide what failure is. Your users decide that for you. So from this, we understand something very important. Failure is subjective. The universe doesn't care if your system works or not. It's oblivious to that. It's our subjective decision when the system is failing or not. And we can change it on the fly, by the way. We can magically... Really? You have SLA? What, sorry? Oh, so if I jump, it happens? Awesome. So the problem with SLA is that, A, not everybody gives you SLA. What's the SLA of Gmail, for example? You give SLA, but you can lie about it, like a lot of people do. So I'm sure that your SLA doesn't include definitions about error rate of every transaction. Or you could return a default answer instead of an error. And that still puts you within the SLA, but you're lying, right? So it's, yeah. יש לי מיקרו לארגן. What the fuck? Okay. We'll just... I think that my connector is, my adapter is bad. Or something like it. No, it's okay. I hope. No, those are. It's not the Mac thing, it's the physical adapter. No.
Is it plugged in the power?
It's plugged in and it's okay. לא רוצה לפטופ אחר ולא שום דבר. זהו, עובד, לא עובד. טוב, שמי שווה לפטופ. שמי שווה לפטופ או משהו. Okay. So the Mac guys are going to save me. Or not?
אתה מתאם.
כן, תעשו משהו. So the problem with SLA is that SLA by itself is not enough, and again, it's subjective. You can like redefine everything on the fly. The easiest way to achieve reliability is to just redefine what failure is, which is exactly what people do when they give default answers, or they cache pages, for example. This is the easiest way to achieve reliability. What, sorry? If you don't catch the error page, if you don't catch the error page, of course, and that also happens. לא, זה לא קונקטור, חבר'ה, מה אתם עושים?
אוקיי, אז הקונקטור הזה בעייתי.
סבבה.
מקצר.
תומר, בינתיים עד שזה. It's like an unwritten law that whenever you talk about reliability, your laptop is going to fail. Yeah. Just click on it and let's go. Okay, so what are the possible states that a subsystem or component can have? Anybody want to answer that? It's a pretty simple question. What are the possible states that a component or a system can be in? Yeah, what's two?
Warning.
Okay, I don't even know what warning is. It's like a weird Nagios concept. So yeah, it could be working okay, or it could be failing. Are there any other possible states? What, sorry? What is flapping?
Not working. Not working.
Okay, so yeah, I'm not actually talking about that. I'm talking about something called fuzzy. Fuzzy means we don't know if it's working or not. We can't define. Okay, because sometimes when we define failure, we have like really sharp definitions for failure. But sometimes we have weird states that we haven't thought about, and we don't know how to classify it. For example, if I've got 3 clocks on 3 different servers, and they're all in disagreement, which one is the correct clock? Which is the right clock, for that matter? We don't know. We don't know how to define it. So it's the same with eventually consistent databases, or when you have split brain. You've got 2 diverging values. Which value is the correct value? Again, we don't know. So this is a fuzzy state. And there's a 4th and very important state, and that is we don't know. We don't know what the state of the system is. And this is really important to remember, because most of the time, our system is not in an okay state, and it's not in a failure state. It's in a we don't know state. For example, you get an alert. Is this a valid alert, or is your monitoring broken? You don't know. What happens if your monitoring fails? Then you don't know what the state of the system is. So it's very important to remember, the absence of alert is not evidence of your system working. It just means that you don't know. That's all. And this is a very powerful concept in reliability. Reliability doesn't mean the absence of failure, okay? So let's talk about failure. Yeah, not this guy over here. So I'm going to present a model, a statistical model of failure. And the first model I'm going to be talking about is statistically independent failures. Now, statistically independent failures is something like mechanical failure of hard drives or servers and so on, and it's the dominant mode in hardware. Okay, most of the hardware failures that we get are statistically independent. There are some statistically independent failures in software, but it's less common than in hardware. What do I mean by statistically independent? If one hard drive fails, that doesn't increase the chance of other hard drives failing. Okay? That's what statistically independent means. There are a lot of fallacies associated with statistically independent failures and statistical independence in general. For example, the hot hand fallacy. So in the office, I've got a Pentium 4 computer that I installed Debian on, and I've set it up as the firewall of the office. And it's been running like without stop, I think without even a reboot for, I don't know, 7 years or so? Something like that. So have I created a system that can't fail? No. Yet every time I go to a company and ask them, what's your uptime? And they're like, oh, 100%, the system hasn't failed. That doesn't make sense, does it? So this is the hot hand fallacy. Just because something hasn't occurred yet doesn't mean that it can't happen. If I flip a coin, the chances of a coin landing on heads is 50% no matter what the result was before. And if I got like 10 times heads, the probability of getting tails is still 50%. Doesn't matter how many times I got tails. So this is a hot hand fallacy. The other side of that is the gambler's fallacy. And you see this a lot with gamblers. Like you go to the roulette table and you got 5 times red. So you automatically think to yourself, what are the chances of getting 6 times red? It's like almost impossible, right? So next time it's definitely going to be a black, right? So no, that's not how statistically independent things work. The chances of getting red are 48% no matter what the result was before. So the lesson here is that past performance does not dictate future performance. You can't really learn, you can't really tell from that. Why do I have an asterisk there? Because sometimes it does. Okay? It does when we're talking about statistically dependent failures. Okay? This is only relevant to statistical independence. So what does it mean in terms of reliability? So first of all, I have to put this slide here. It's like a small sidetrack, so we'll know what we're talking about. Those are common reliability measures that we see in specifications of hardware and software. Mean time between failures, the rate of failure, the probability of failure, the reliability, which is just 1 minus chances of failure. This is something that you often see on hardware. A typical MTBF, for example, on a hard drive is like something like 150 years. Anybody say something weird here?
I haven't seen one that hasn't been.
Yeah, for example. So I don't know about you guys, but I don't think that anybody has operating experience of 150 years with a hard drive. We haven't even started producing them like before 30 years ago. So how do you get to that number? No, you don't lie. This is not a lie. No, okay, yeah, big numbers. So what hardware manufacturers do is they take a large bunch of disks, say 10,000, they run them in a lab for, say, 3 months in some kind of typical workload, and then they extrapolate the numbers from that, okay? So this is why I showed the fallacies before, because you can't tell from a single device averages. Those numbers are averages. 150 years between failure is average over a large group of drives. It doesn't mean that a single drive won't fail in 2 days, okay? That's very important. So serial reliability. Serial reliability is a system where we have a few devices, a few components connected in series. And the failure of even one device or one component is enough to crash the entire system. For example, we have a web server connected to an application server connected to a database. If the database fails, the entire system fails. If the application server fails, the entire system fails. The total reliability of the system is simply the product of the reliability of all those components. So what does that mean in practice? So suppose I have a system with 3 components, one that is highly reliable, 0.995, one that is a little bit less reliable, 2 nines, and one that is low quality, 0.95. The overall reliability of the system is 0.936, which is not very high, okay? So the question is, what should we improve? Anybody want to take a guess? Which component should we improve? The weakest, right. If we improve component number 1, which is the most reliable component, we get a very, very small improvement, almost no improvement at all. If we improve component number 2, we get a slightly larger improvement, but still not a very big improvement. We improve the worst component, we get 3 times the improvement in terms of failure. So, 2 things that we can learn here, actually 3 things. 1, the total reliability of a serial system is always less than that of the worst component. The second is that the best return on investment comes from improving the worst component. And this means that after we improve that component, we have to look at the system again and see if this is still the worst part. And if it isn't, then we have to move to another component and improve that part. And this is, yeah, like this one. And this is very important, and this also means that improvement in a serial system is very, very expensive. And this is why people go to clusters, right? Because serial system is very expensive. So let's talk about clusters, about parallel systems and redundancy. So the mathematics of redundancy, this is like the equation. If you know what this means, this is the binomial product, if you care about those things. But what does this mean in numbers? So you see up to k failures? That's the number of failures we can tolerate, and n is the size of the cluster, if you will. So let's take a redundant system, a cluster of 10 machines, that can suffer up to 2 failures. 2 servers can fail. If the components, each server has 95% uptime, okay, MTBF is 19, and you can see that the improvement is by factor of 4.5, which is a lot bigger than a serial system. But if we take better hardware, say enterprise-grade hardware, then the improvement is, huge, 88.7. It's insane. So you get better return on investment if you use high-quality components. Does that sound weird to anybody? Why is everybody using commodity hardware then? Yeah, you can buy more of those. So this is the improvement you get without changing the size of the cluster. Okay? What happens if you can change the size of the cluster? So suppose we have a redundant system, yeah, or a non-redundant system that it is with my laptop. Yeah, try it again. Okay. Or if I just don't move, then maybe it would be better. Or if I don't speak, or if I don't breathe, or whatever. Yeah. So 0.95. And let's see what happens if I can tolerate only 1 failure. You can see that in a cluster of 10 machines with only 1 failure, the reliability is actually worse than that of a single machine. How is that possible? What did I get by clustering then? If I use 2 machines, then my reliability is improved, and it's actually better than a single machine. But the overhead, you see the overhead there? I'm actually wasting 20% capacity of the cluster. That's horrible. Think about what happens if you use a cluster of 2 machines. You're wasting 50% of your capacity. That's not economical in any way. So what happens if we enlarge a cluster? If we use, say, 100 machines, and we only allow for 5 machines to fail, our overhead is very small, but our reliability is horrible. If we use 9 machines, then our reliability is now bigger than a single machine, and we've only wasted 9% of the cluster. If we use 11 machines, then at the price of 11% overhead, which is a lot smaller than the cluster with 10 machines, we achieve very, very high reliability. And this is why we want large clusters. They are more economical. But this is the important part. If you go and use large clusters, you can't use the n+1 rule that everybody uses. It's only true for very small clusters. You need to use percentages of redundancy, and they have to be, in terms of absolute machines, pretty big. Otherwise, you can actually reduce your reliability. Okay? This is also why it's very important to replace failed machines very fast. So let's talk about statistically dependent failures, or correlated failures. This is the dominant mode in software, by the way. Most of the failures we get in software are actually correlated. So correlated means that the failure of one component can actually increase or decrease the probability of other components, of the failure of other components. Why would this happen? For example, shared workload. We get the same load on all the components. For example, I had a load balancer that failed when its counter reached max integer, and 4 hours later, its partner, the standby, also failed. Why? Because they had the same workload, so the counters, reached the same number around the same time. So this is what correlated failure means. Okay? So what can we do about that? How can we avoid that? Ideas? This is a really big problem for clustering. Okay? This can actually pretty much take away all the benefits you got from clustering. So what do we do about that? How do we solve this? Okay, less dependencies, right? Something else? Randomization, yeah. We have to induce variance into our systems. For example, in the case of the load balancers, I started rebooting them at different times, so the counters won't have similar values. We can use devices from different manufacturers and so on. Okay? We can also segment our systems. So this is the law I should be using. And this is very important because a lot of people get this wrong. Backup and operational subsystems should avoid coupling with primaries. And people get this wrong, especially in the context of monitoring and operational systems. For example, people often let their monitoring system use the same database as other production systems. This is horrible. For example, coupling your deployment tool or tools used for debugging with the primaries. Those tools are going to be used when there is a failure. They cannot share infrastructure with their primary system. Okay? So let's have a riddle now. So suppose we're talking about the police pulling over drunk drivers for tests, or drivers for tests. And 1 out of 1,000 drivers is drunk, and the breathalyzer, the device we use to test drivers, has false positives of 5%. But if you test a drunk driver, it will have 100% success. Okay? And we pull the driver at random, and the breathalyzer showed that the driver was drunk. What is the chance, what is the probability that the driver is actually drunk? And remember, the device has shown that the driver is drunk. 2%? What? 95%? 95%? 2%? Okay, so we've got two answers here, 95% and 2%. Who thinks it's 95%? Show of hands, come on. Who thinks it's 95%? 1, 2, 3, 4, 5. Okay, who thinks it's 2%? 4 people, and everybody else doesn't think it's anything, obviously. Okay, so the answer is 2%. If you thought that this was 95%, you have fallen for the base rate fallacy. What is the base rate fallacy? And why is this 2%? Because out of 1,000 drivers, about 50 drivers are false positives, and only 1 driver is actually drunk. So we've got a bias of 50 to 1 favoring false positives. The base rate is 1,000 to 50, and this is what we ignored. Why is this very important in reliability? So think about the failover of databases, for example, active-passive failover. We've got the controller that is trying to detect the failure of the master. And unfortunately, the controller also has false positives. Sometimes it detects a working master as non-working and tries to fail the system. What are the chances of the failure being a good failure, meaning that the master actually failed? Turns out they are very, very low. About 95% of failovers are bullshit, bogus failovers. Should not have happened. And if a failover was not associated with other failures, for example, if we couldn't introduce inconsistencies during the failure, that would be okay. But unfortunately, with the systems like MySQL, with master-slave failure, failover, the failure itself can cause new horrible problems. So what do we do about that? How do we deal with this? we either disable automatic failure, greatly reduce the number of false positives of the controller, which is very hard to achieve, or favor active-active systems. And this is one of the reasons why people prefer NoSQL solutions, or things like Galera, MySQL Galera. Let's talk about multiple dependencies. This is very common in microservices environments. We have a component, an application server. The application server has, let's say, 0.99 availability. But unfortunately, it has dependencies, each talking to 3 other services, which also have reliability of 99 each. This reduces the reliability. Remember, it's a serial system. The failure of one dependency can fail the entire system. This reduces the overall reliability of the system to 0.96. What happens when we add another layer? Because those services also have dependencies. We reduce the overall reliability to 0.88. That's horrible. Now think that in microservices with 400 services, we can have 4, 5 layers, 40 layers. This totally destroys our reliability. So how do we deal with this? Ideas? Yeah, whiskey is a good solution. Other solutions? Anybody? Circuit breakers, right. So what circuit breakers do is they disconnect a failed component from the system and return a default answer instead, so that the failure of one component does not fail our entire system. And if you have a lot of dependencies for your systems, this is a must-have. You can't have high reliability without it. Let's talk about queuing theory. This is known as the MD1 model, not that anybody cares, but most queues work somewhat like this. The delay, the latency in a queue is proportional to system utilization divided by 1 minus the utilization of the system. If your system is fully utilized, then your utilization is 1. And as you can see, I don't know if you can see the number, but this right here is about 80%. Starting at 80%, your latency is just going through the roof. This means you always have to avoid going over around 80% capacity. If you do, your quality of service is going to be horrible, and you will have failure. This is why it's very important to throttle your system. So this is a server, a backend server, and the frontend server. This is frontend, this is backend. And the frontend server is pushing traffic to the backend server. What happens when the backend server has too much traffic? It starts timing out, but before that? Backlog. Yeah, backlog. Load starts queuing inside the server or in the interconnection on the socket. What happens to latency? It's going through the roof. And eventually, we will have failure. How can we avoid this? Queuing mechanisms only make latency even worse. They only push the problem to later time. If you don't have capacity, you don't have capacity. You can add capacity, but that takes time. Yeah. What do you do? But you can't queue everything. If it's a user-facing transaction, you can't queue it. So what do? Flow control, right. You do back pressure. You start pushing back. This is a mechanism that's very common on blocking infrastructure, not so common in non-blocking technologies like Node.js, but you still have to have it, because otherwise you have no way of telling the front-end part that the back-end is loaded. So no matter what kind of mechanism, no matter what kind of system you have, when it's composed of multiple parts, you have to have back pressure within your entire system to just push load back and let the users know that somewhere in the system there's a part that's overloaded. Otherwise, you will have internal queues filling up. Another very nice thing about queuing theory is something called Little's Law. This is one of the basic laws of queuing theory. And Little's Law says that in a system, in a stable system, regardless of the distribution of the load, this rule here will hold. L is the number of clients in the system. Lambda is the arrival rate, or the applied load, and W is the latency. Okay? And if we have a load balancer, this guy here, which is working according to the most common algorithm, which is list connections will try to make, the L of different servers equal to each other. The number of connections they hold should be equal to each other. This means that latencies, okay, are proportional. The proportion of latencies is proportional to the throughput of different servers. This is what we want from load balancer. We want all the servers to get roughly the same throughput, right? So what happens if one server fails? And, for example, starts returning errors very, very fast. Suppose the normal latency of the system is 100 milliseconds. Now we've got a failure in one server, and it returns 500 errors in 1 millisecond latency.
Close more connections than the number.
Exactly. If the latency goes 100 times, it's going to be 100 times lower, then the throughput will be 100 times higher. This means that one failing server can take about 90 or 95% of your traffic. So one failed server in a 10 server cluster can cause 95% failure rate. That's insane, right? How do you avoid this?
Better check.
You will still catch it later. So what do you do? Throttling, right? You throttle. And it's very important to set the throttling rate according to the normal rate of the servers. Okay? Otherwise, you won't do anything. You won't achieve anything by it. Yeah, technology is broken. I should move. This is like almost the last slide. Okay, so feedback loops. Feedback loop is an example of what happens in a complex system when you apply local logic to it. I'll give you an example. If you try to get to be overheard over a noise, you try to speak in a noisy room, okay? What do you do to be heard? You lower your voice, and you raise your voice, you scream. What happens if everybody uses the same algorithm? The noise level goes up. So you scream even harder. But everybody screams even harder until everything blows up, okay? This is a feedback loop. And feedback loops, this is like the mathematical example of a feedback loop. To avoid them, we have to use backoffs and cooldown. Because if all the servers employ the same recovery algorithm, which causes feedback loop, we're going to have horrible things. For example, anybody had a retry storm? Yeah, a couple of people here. A retry storm, think about you have a 1 second outage. What do all your clients do? Hit retry. So you get a surge of load that hammers all of your servers. The system is again down. Everybody retries again, and this goes on forever. And sometimes even increases. So what you do is you back off. You wait longer and longer between retries, okay? Or you do cooldown. You stop the load until everything stabilizes. Those are mechanisms that are very, very important to have in place. Otherwise, you won't avoid feedback loops. So, the key takeaway here is that reliability is important, and you have to put it in all the layers. You have to put it in the back end, you have to put it in the front end, you have to put it into the mindset of the product and everybody else. You cannot achieve reliability if you think it's somebody else's responsibility, if you try to delegate it. It's impossible to delegate reliability. If you think it's ops problem, you will never have a reliable system. So thank you very much. And if anybody wants to ask a question. No time for questions?
2 questions.
Okay, so 2 questions. Anybody want to ask a question? Short ones? Nobody? Okay. Have fun.